96. The HELOGICOFEFFBCTS. Let us first look at the interaction of the factors. It comprises three elements. 1. An active factor, or a factor of derivation, the regulating factor. 2. A factor of application, the regulated factor. 3. An action of the regulating factor on the factor that is regulated, in other words, interaction. LET thus accept TWSOUTPROOFTH. The interaction has a sign given by the algebraic product of the signs representing 1. The direction of the factor of derivation, 2. The direction of the factor of application, 3. The direction of the action on the factor of application, this being positive when the absolute values of the two factors vary in the same direction, negative in the opposite case. For example, a positive factor acting on a negative factor in the positive direction gives a negative interaction. One might say, F on by F equals. The interaction is represented by an arrow joining the regulating factor to the factor which is regulated. The plus and the qualifying the different arrows give the direction of the factors and of the interaction itself. The sign of the action relative to the two factors is given by a positive or by a minus sign near the end of the arrow symbolizing the interaction. Thus, automatic film printing device constancy effector. The useful effect of the effector is to make positive prints of the film. The goal is to obtain positives of an optimum and regular density. There are three factors. A negative film of very irregular value according to the pictures, a positive blank. 97. The HINKINGDYM film free from specific reaction for any one emulsion and a variable lighting source, easily regulated. The irregular negative interacts on the variable light in order to give the regular positive. Before the negative comes into contact with the blank positive, the beam of light shines through it onto a photoelectric cell which translates the opacity of the silvering into an electric potential which, through amplifiers, is able to govern the light intensity by rheostatic control. The density of the negative image negative factor acts then on the light positive factor. This action has a positive sign since the light increases when the density of the negative increases. We have then, on F by F equals. The regulation is thus obtained by a negative interaction. Let us note that it is a question of an effector that has achieved its goal, a constancy effector. Windmill for pumping water with constant EFFVCTCONSTANCYEFFVCT or a windmill for pumping water may be required to produce a constant electric current. The variable factor, whose variations it is necessary to compensate, is made to act on a factor which it is possible to regulate. The variable factor here is the wind whose force is concentrated by a funnel. The factor that can be regulated is a resistance controlled by a rheostat whose position is itself controlled by a plate on which the air currents impinge. The stronger the wind, the greater the resistance and the less current is sent out by the dynamo for each revolution of the windmill, but, as its speed increases, the output of energy remains constant. 98. The HELOGICOFEFFBCTS. A positive factor the force OF the wind acts positively on a negative factor. We have thus, F on, by plus. As in the preceding example, although the factors have opposite signs, the interaction is negative. We would emphasize that there again we are dealing with a constancy effector. Another solution to the same problem is given by the windmill whose speed is diminished by an increase in force of the wind. For a gentle wind the inclination of the vanes is at its optimum value. For a strong wind this inclination must be altered to reduce the speed of revolution. Here the two factors are positive force of the wind and favorable setting of the vanes, but their relative action is negative, that which gives plus on plus by equals. Thus, in three cases of a constancy effector, there is negative interaction although the signs of the factors combine differently. It would seem as if we have here an indication of a general law. Let us see what happens in the case of a constancy effector. As an illustration we will choose an example that is very like the preceding ones. Windmill with a maximum effect tendency effector. A windmill takes its greatest advantage of the wind at a setting produced by the wind itself acting on a tail vane. This is expressed in the following diagram where a bar beyond plus R plus plus percent plus 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 F windmill plus I plus vertical line backslash tail vane J power 99 the HINKINGDYM the CHINE. The arrow of the effector shows that the effector is a tendency one. The force of the wind positive acts on the factor of unfavorable direction negative, causing it to decrease when it itself increases. Thus we have plus on by equals plus. Contrary to the foregoing cases, it is a positive regulation. The importance of this example following after the others can be appreciated. If the effector windmill is to maintain its effect towards the value of the attained goal instead of tending towards a goal that is not attained, ought not its regulation to be in a contrary direction, that is to say negative. But since the goal always remains beyond the reach of the effect obtained, the negative sign of compensation does not enter into the question, instead it is the positive sign of the maximum effect. We naturally ask if regulation by interaction ought not to have a different sign according to whether the goal is or is not attained. If we come back to the example of the automatic printing apparatus, we can show that this intuition is not unfounded. The goal of this effector is to obtain, despite the variable density of the negative, a constant depth of exposure in the positive, the elimination of the differences of density during the process of printing. If we could imagine the absurd proposition that, on the contrary, we might wish to accentuate the differences in exposure of the negative, then the underexposure of the negative would be more accentuated in the printing than it was originally. The negative that was too dark would give a positive that was lighter than the most unskillful of human operators could ever produce. The effector would then be a tendency effector, since its aim would be to obtain the greatest possible difference of silvering. To obtain such a result it would suffice to invert the negative action of the light, that is to say to diminish it where it increased, to increase it where it diminished. We should then have a positive that would be the blacker the more that the negative was underexposed and vice versa. The irregularity of the positive would be still more accentuated towards its maximum and the effector would tend towards its goal. Its regulation, if one could call it that, would be on F by equals, that is to say, it would be a positive regulation. IU. The HELOGICOFEFFBCTS. In the same way, if, in the windmill producing a constant supply, we were to invert the direction of the action of the wind on the rheostat, we would have an interaction F on by equals F. It would result in absolute chaos. When the wind blew with gale force, the rheostat would provide low resistance and the dynamo would burn out. When there was only a very gentle breeze, the resistance would be a maximum, and the current practically zero. For the cases which we have expressly quoted as being absurd, a tendency effector would be regulated by a positive interaction. From now on we can postulate a law of interaction. A negative interaction regulates a constancy effector and disorganizes a tendency effector. A positive retroaction regulates a tendency effector and disorganizes a constancy effector. Regulation by REDROACDION. Regulation by retroaction is the regulation of a factor by energy arising from an effect. It is the feedback which guarantees an effect against the variation of its factors. Three elements participate: 1. An active effect or an effect by derivation, regulator, to a factor of application which is both regulated and at the same time regulating. 3. An action of this effect on this factor, the retroaction. In principle, retroaction consists of a function relating an effect to its cause. In practice, it consists of a chain of effectors, one of which plays a role of detector and the other of reactor. Let us try and distinguish, as we did for interaction, the laws that a retroacting regulator should satisfy. Can the feedback be applied to any factor whatever? In principle, it can. In practice, certain general rules must be complied with. The factor should be capable of being regulated. It should have a high coefficient of efficiency and it should act as near the output of the system as possible. Often these qualities are irreconcilable. Here are two examples drawn from the motor car. 101. BHINKINGBYMCHINE. Our most modern cars have only two sorts of feedback, both of which are derived from the speed of the engine, acting either on the ignition control or on the gearbox. The ignition control has rather a low coefficient of efficiency and the feedback has rather a feeble compensatory power. But the gear ratio factor, whose influence is certainly very considerable, is on the other hand not very easy to regulate, or at least its regulation, the substitution of one pinions or another, requires an energy that is fairly considerable. The detector has practically no mechanism capable of appreciating the variations of speed except by centrifugal effect. The whole difficulty lies in making this effect, which is always minimum, react on an awkward regulation factor. This is what accounts for the difficulties in the problem of automatic gear changing, and this is why the internal combustion engine has difficulty in adapting itself to the changes in speed of its effects. Its regulable factors are not efficient enough and its efficient factors are difficult to regulate. But the situation would become quite different with the introduction of injection motors, as the quantity of explosive mixture is both an efficient and regulable factor. As in the case of interaction, retroaction can be positive or negative. Its quantity is given by the algebraic product of the signs representing 1. The direction of the effect of derivation, 2. The direction of the factor of application, 3. The direction of the action of the effect on the factor of application, this being positive when the absolute values of the effect and the factor vary in the same direction and negative in the opposite case. It is important to note that the direction for a retroaction remains the same whatever the direction chosen for the useful effect. In fact, the direction for the factors changes if the referent sign changes. Some examples will serve to show that retroaction, just like interaction, regulates or upsets the effectors according to whether it is negative or positive, according to whether the effector is a constancy or tendency effector. Here is the case of a constant level reservoir, the two diagrams of which are based on an effect which has been arbitrarily 102. The HELOGICOFEFFBCTS chosen as being in a different direction for each lower level and higher level, yet each diagram shows that the retroaction is in a similar direction. Plus on, by plus equals plus on plus by equals. Another example of a constancy effector is the furnace with an automatic draft control which is retroactively regulated. We now have a case still with a constancy effector that has a negative regulation where the reactor acts negatively on the application factor, which should therefore be considered as being a positive prefactor. In other words, the anti-fading device, which can be expressed in two ways. 103. The HINKINGBYM Let us pass on to the case of a tendency effector. These examples are much less common. Let us take the case of the automatic regulation of ignition control on many of our cars. The engine sets its own advance of spark, its speed of rotation acting by counterweights whose centrifugal force alters the position of the distributor arm relative to the contact breaker. The faster the engine turns, the earlier spark it will have and the faster it will continue to turn. It is positive retroaction, the action tending towards its maximum. The F regulates the tendency, giving it new spurts of energy, whereas the regulates the compensation, stabilizing it. But according to the foregoing, it would seem that the ideal condition would be always to advance the spark as the speed increased. But, for a given speed, the admission of mixture, that is to say the position of the accelerator, may be very different, so that a slight adjustment to the spark control can usefully be made according to the variations of this factor. Suction of the cylinders or partial vacuum in the inlet manifold. In some carburetors, that are not in very general use as yet, the ignition control is submitted to another regulation that is independent of the first one, capable of opposing it and compensating it. The regulation depends on the partial vacuum in the inlet manifold, acting on the membrane of the manometer. This ingenious mechanism is difficult to analyze, in fact almost impossible without the aid of a diagram making the idea more accessible. A positive interaction acts negatively on deviates a XXX plus MOT plus minus 1 AJ speed of revolution circumflex accent CO circumflex accent ESS degrees duo regulation compensator retroaction plus ON plus BY plus equals plus interaction ON BY equals plus 104. The HELOGICOFEFFBCTS, a factor which is regulated by the speed, in other respects, through a retroaction which is not only positive but also has a positive action. This example shows admirably the advantage that the technicians would have in logically analyzing the effectors that they employ and construct. Analysis which gives results for certain techniques would be worth perfecting for other techniques. Before searching for a practical solution, it would often be worthwhile solving problems by the method of the logic of effects. More complex cases. Let us examine an interesting case showing a feedback which compensates a natural retroaction leading to disorganization, that of carbon arc lamps, in which the distance between the carbons is regulated automatically. The functioning of the arc wears the carbons so that the current will diminish to a point where, finally, no more will pass. The effect of wearing a secondary positive effect retroacts on the distance negative factor between the carbons by increasing its positive action, so that we have plus on, by plus equals. The retroaction is negative, it upsets a tendency effector. But on the same factor the feedback is applied, which, being derived from the component effect of intensity, retroacts on it by means of a system of solenoids diminishing the distance as the current increases. This feedback is plus on, by, equals, thus regulating the tendency effector. Distance between carbons. 105. DHINKINGDYM It is satisfactory to see clearly in this mechanism how a device may act in the opposite direction to a natural disorganization. Let us go on to the analysis of the Watt governor. This typical feedback proves to be quite a special case. A careful analysis shows that the steam engine can equally well be considered as a constancy effector or a tendency effector. Constancy effector. One can't look upon the steam engine as a machine which gives a constant speed of rotation whatever the load, which is, of course, one of the factors. The speed of positive effect by definition retroacts through the medium of the centrifugal force of the flight weights on the factor steam inlet positive in such a way that the factor is diminished when the speed increases and increased when the speed diminishes negative action. Hence, F known plus by equals constancy regulation. Tendency effector. But the same machine can be seen as a tendency effector to lift the maximum load. The global effect of the energy may be broken down into two component effects. 106. The HELOGICOFEFFBCTS. Load and speed. The load, the useful effect, is positive, but the speed, which diminishes when the load is increased, is negative. The feedback is derived from this speed component in order to have a negative action on the admission of the steam. We have then, on vertical line, by, equals plus, tendency regulation. The universal law of regulation. These examples would enable the postulation of a law of retroaction which is similar to that of interaction. But we must unite these two laws in a much more general formula. Every constancy effector is regulated when a factor or an effect acts on a factor in such a way that the product of the signs of the factor for the effect of derivation, of its action and of the factor of application is positive. It is disorganized when the product is negative. Or, if we take the various definitions for granted, every constancy effector is regulated if it is submitted to a negative interaction or retroaction. It is disorganized if the interaction or the retroaction is positive. Let us accept this law as being experimentally true, holding its demonstration in reserve. But let us understand from now on the importance of this dual direction of the regulation, whether it be a question of increasing an effect to its maximum or to its minimum, or whether it be to maintain it at a certain value. Cyberneticians have seen feedback only in the light of constancy regulation. Then they say that a negative feedback annuls the deviation of effectors. It is perfectly true for constancy effectors, but untrue for tendency effectors, which have not been distinguished from the former. Regulation is a perpetual battle between deviations, but, in the case of the tendency effectors, it is positive feedback which without annulling them, since, by definition, these effectors never attain their goal, tends to diminish them. One might suggest that this law is self-evident, but we should remember that we have applied it to the actions of mechanisms that are already well known, since they have been determined by us. But if, on the contrary, it were to be applied to data that 107. DHINKINGDYMCHINE have been very little studied and are incompletely understood, or inaccessible to study, then the law would show itself to be an admirable means of penetrating such phenomena. If we could think of biological regulations along these lines, or of the regulation of the nervous system, which probably depends on it, we should find their comprehension greatly facilitated by the use of these logical methods. Interaction and REDROACDIO, and the essential character of retroaction is to bring the effect back to a given value, whatever may have been the origins of its variations. But what do we mean by interaction? Let us come back to some typical examples. In the automatic film printer, if the sensitivity of the emulsion varies, the print will become accordingly either more or less dark. The regulation was provided for a given sensitivity of the blank film. For a different sensitivity, a different regulation would be necessary. The interaction has protected the effect from the variation of one factor only, that of the density of the negative. With regard to the windmill with constant effect, if we were to measure the amount of current that it produced after a period of some years, we should certainly find it very different from that originally intended by its constructor. The gearing would have rusted and the magnets of the dynamo would have changed. Interaction therefore does not guarantee the effect against variation of all the factors. The only factor whose variations do not influence the effect is the factor of derivation. In this case it is the force of the wind, and in the other it is the density of the negative. Let us imagine a windmill regulated by retroaction. A feedback would detect the variations of the voltage produced and would regulate the resistance accordingly. The effect would be much more regular than that of an interaction. It is obvious then that it would be worthwhile for an engineer to solve the problem by logic before embarking on a practical solution. So it is desirable to lay down a principle, which, in a pragmatic guise, hides, as we shall see, the very important logical implications. 108. The HELOGICOFEFFBCTS. Interaction can only regulate an effector in relation to the variations of one factor, the factor of derivation. Retroaction regulates an effector in relation to the variations of all the factors. It would seem as if retroaction always carries an enormous advantage, but interaction still has its points. The following is a diagram showing retroaction. The effect T acts on the factor A. The message is the function of the variations which, originating in B, have affected B. The same applies to the factor C and moreover for the factor O which has corrected its own variations. But outside these intrinsic variations of A, the message also reflects those which represented the correction of the effect of the preceding moment. We see then that the feedback regulates the factor B according to past information. The delay in regulation of retroaction is inherent in its basic principle. The retroactive message of time t depends on the retroactive message of the time t, e. This is the concept that in other sciences is known as hysteresis, extending the application of a term that belongs really to magnetism. Why should not the sense of this term be extended still further? All regulation, whether it be manual or automatic, acts only with a certain delay of efficiency. This is the time taken for the correction of a factor to make its influence felt on the effect. This delay depends on whereabouts in the system the regulation is applied. The nearer to the output of the mechanism that it is applied, the shorter the delay. It is in fact the time elapsing between the moment that a factor acts and the moment that its result becomes apparent in the effect. But, in addition to this delay which is manifested as in all regulation by interaction and which is mostly negligible, retroaction suffers from its own delay which we propose. 109. The HINKINGBYMCHINE. To call hysteresis, the time necessary for a variation of a factor to make its influence felt on the regulating factor through the effector, the effect and the retroaction. In the sketch on the previous page, the delay in efficiency is represented by the path of A, hysteresis by the path B or CA. Regulation performed by hand seems to have only one delay of regulation, the delay of efficiency. In reality it also has a hysteresis, but a human one, the delay in action of our senses detector of our nervous transmission message and of our muscles reactor. But it goes without saying that the hysteresis of a good machine is smaller than that of man, without even taking into account our worst disabilities, inattention and fatigue. Let us define these different terms. In an effector, the delay in efficiency is the delay which elapses between the moment when a factor undergoes a variation and the moment when the effect receives its influence. In a retroactive effector, hysteresis is the delay which elapses between the moment when a factor undergoes a variation and the moment when the factor of application receives its influence through the effect and the message. One can define error of hysteresis as the difference between the effect which would be produced if the retroaction depended only on the value of the factors at the moment t and that which happens in reality due to the influence of the value on the variable factor at the moment t, e. Delay in regulation comprises two elements and both have to be fought against. For delay in efficiency, this is possible. It can be diminished by applying the regulation as near as possible to the effect. But for hysteresis, it is quite a different matter. One might diminish in vain the chain of effects by which retroaction takes place. One might equally battle in vain against the inertia of the different components, because it is necessary that the variation of a factor should upset the effect in order that the effect should send back its corrective message. The rolling mill whose feedback corrects the effect that has already been accomplished does not suffer from any delay in efficiency. It only shows hysteresis, the time between which it discovers an irregularity in the sheet metal and acts upon it accordingly. The error of hysteresis is the amount of variation IIO, the HELOGICOFEFFBCTS, of thickness in the sheet metal which is able to exist on account of the small time lag of the correction. Obviously an interaction has some delay in efficiency. In order to comprehend it, we may imagine the following absurd idea, that in an automatic film printing apparatus, the regulation, instead of acting on a rheostat, acted on the floodgates of the turbine producing electric current. On the other hand, interaction possesses no hysteresis. Actually, it suffers from a slight delay of its own. In the sketch below it is seen in the difference between the paths of E and E, or, more exactly, between the delay in action of it on E through B. But this delay can be disregarded. 8. B. Interaction and retroaction compensate for each other's defects and advantages. Interaction adapts the effect to the variations of a single factor, but acts without hysteresis. Retroaction adapts the effect to the variations of all the factors, but acts only after a certain delay, the delay of hysteresis. 111. CHAPTERVI. Retroaction, the secret of natural activity. OUR radio sets compensate for fluctuations in signal strength and reduce the gaps in the reception due to fading. The very weakness of a signal received will cause amplification, and if the signal is too loud, its strength will be toned down. Thus any deviation from normal leads back towards normality. Herein the machine realizes the concept of goal-seeking. In the case of living organisms, such a faculty may often be likened to an intelligence inherent in the species, or a part of the mechanism of life itself. Its amplification is either stronger or weaker according to the requirements. It is the final goal set by the constructor for the machine which governs its own activity, the effect of such activity influencing the factors so as to maintain stability. Thus the machine of today has overstepped the field of action assigned to it in the 19th and early 20th centuries. One cannot but marvel at this automatism when one comes to examine it closely. All causes of error are corrected without its being necessary for man to analyze their nature or even to recognize or suspect their presence. It is the error itself which corrects the error. It is because it has deviated from its route that the automatic pilot is able to remedy this deviation. In the case of the machine, as in the animal, error is a generating force. It conditions its own correction. All stabilization is effected by feedback. If we extend this argument still further, we shall find that it is the existence of feedback in living organisms that gives error its constructive power. This is surely what we understand by the mechanism of experience. The way in which life extracts from ill its appropriate antidote can only be fully realized when we invoke the principle of feedback. Whether it be a 112 question of temperature regulation, the pH of the blood, or the urea content of the blood, or whether it is necessary to expel a foreign body from the eye, nose or throat, it is the deviation from normality that causes the secretion of some hormone or other substance or causes some reflex mechanism to act in order to combat the imbalance. All microbic disease gives rise to a retroaction designed to restore the equilibrium that had been disturbed. Always the remedy is roughly proportionate to the disturbance which it combats. Claude Bernard gave a striking proof of his genius and clarity of vision when he said, "The stability of the internal medium is the condition for the existence of free life." The further living beings evolve, the more they achieve independence in relation to external environment. Apologize if it is swept by the currents into water which is either too hot or too cold. It is not free. The Coelenterata and the Spongifera have no internal media. The echinoderms have an internal medium which is in communication, however, with the external environment. The internal medium is sealed off in the Annelida, the mollusks, and the arthropods, but the liquid filling the cavity is not part of the organism. In vertebrates the plasma plays an analogous role, but the blood and lymph are living tissues. The animal is its own internal medium, and it keeps itself stable. Pierre Vendrais elaborates the ideas of Claude Bernard in a book which shows a cybernetic approach before the science was formulated. In his book Via Probability he claims that independence is achieved by the organism due to its faculty of being able to disengage itself from external events, so that it does not become the plaything of fortuitous external changes. He sees in this stabilization against chance events an illustration of probability which will be discussed in the following chapters. If we run We require an increased supply of oxygen, just as the Watt steam engine requires more steam when it has a bigger load to shift. An analysis of what happens, by the method 1-2-1 long before cybernetics was talked of, Herter, an American physiologist, gave as a definition of illness the signs of reaction against any noxious agent. 2 Albin Michel, 1942. RETROCTION, THEFECRETOFNATUR 3. DHINKINGBYM of the logic of effects, shows that the effect to be stabilized here is the concentration of C02 in the arterial blood. The respiratory center in the medulla acts as the detector element in the system, starting off faster and deeper respiration as soon as the CO2 level in the arterial blood is increased. This increase of level is accompanied by an increase of lactic acid in the venous blood, which is the measure of the previous increase in muscle activity. In this book, however, we do not propose to deal with the human organism, which will be the subject matter of a future book on equations. What is remarkable is that the mechanisms of the nervous system make use of the same principle. Without attempting proof for the moment, we will here affirm that feedback governs all our movements. It is due to feedback that the adjustment of our movements towards their objective is possible. Let us consider for a moment the movements of the hand if we wish to pick up a needle lying on the table in front of us. The action designed to pick up the needle follows a smoothly running sequence of appropriate movements. But in certain diseases the action will be clumsy, spasmodic, and will degenerate into a tremor, intention tremor. In another type of nervous disease the movements will be wildly inappropriate and suggest that the nervous system is without information as to the position of the limbs, ataxia. The effect of the absence of an organ may often furnish a demonstration of its utility. In these pathological cases, the functions of the nervous feedbacks are rendered apparent by the effects of their breakdown or incoordination. The study of nervous disease showed the early students of cybernetics the parallelism between nervous activity and that of electronic mechanisms. In the first group of cases cited, the intention tremor is due to disease of the cerebellum. In the second, the ataxic incoordination is due to interruption of the ascending tracts in the spinal cord. We are entitled to assume that in both cases retroactive circuits governing the movements have been affected. This hypothesis in the hands of the earlier cyberneticians was a fundamental step in the application of the new science to the nervous system. The scheme of motor regulation can be sketched in which the effect is the movement, the detector the sensory proprioceptive system which informs the nervous system as to position and tension of joints and muscles. The message conveying this information ascends in the proprioceptive tracts and the factor that is modified is the motor discharge. The movement taken as a whole is regulated by the distance that separates a limb from its objective. Another type of control, visual control, works in with that of the proprioceptive system. The eye detects the relation between the movements achieved and the objective. Sufferers from ataxia endeavor to supplement their defective proprioceptive sense by sight, but sight in itself is unable to compensate for the deficiency in full. It would seem, then, that before the advent of the machine age all work was regulated by a feedback system operating in man and animals. When an ox pulls a cart, if the resistance to the wheels is increased by some incline or a stone in the way, the animal reacts by an automatic increase of traction, just sufficient to overcome the difficulty. Our motor cars without a truly automatic gear change are in this respect inferior to the animal form of traction. In the early times before the advent of machinery, all were benefited by the power of adaptation that has generally been claimed as the irreplaceable advantage of animal or manpower. Machines which had no feedback were at a grave disadvantage. The least task requires to be regulated in terms not only of what has already been done but also of what there is yet to be done. It is always necessary to record the effect, to detect any deviations and to react according to the deviation by the modification of our movements. Observations are made by the sense organs and communicated by the afferent nerves to nerve centers that estimate any deviations from the norm by reference not only to acquired, but also to innate, sensory structure. The operation is carried out by our hands. Here is a feedback system. All reflection may be understood as an example of the effect retroacting on the cause. Even the etymology of the word suggests this. An effect is contemplated in advance by the mind and its relation to the goal is estimated. Thence the nearest approach to the ideal is made possible, by correction of the factors involved. Memory itself can be represented as registration of retroactive messages analyzing effects according to their success or failure. RETROCTION, the HEFECRETOFNATURIDLCTIVIVY. 5. THINKINGBYM The machine without a feedback would be incapable of acting on its own. It would be absolutely ataxic. If left to itself, it would be limited to a program determined for it by the operator, and the occurrence of any unforeseen circumstances could not be met by any adaptation. Its master would have to guide as he might a cripple. In reality, of course, he supplies the feedbacks that the machine lacks. When he detects certain deviations from the goal, he is able to govern the machine as a whole, by acting on certain factors that were left designedly free by the constructor. Such a machine constitutes the reactor in a man-machine complex governed by retroaction on the part of the man. When the first true machines made their appearance, the genius very soon invented feedback. What created his governor, not by theory, not by logic, but by the instinct of a technician. This at any rate is generally admitted by the new science of cybernetics. One may doubt whether all work before the advent of the steam engine was governed by human or animal feedbacks. Surely use was made of one natural agency, however irregular in action, the wind. It was even more important for a windmill to find ways of adjusting itself to gales and breezes than for a steam engine to respond to variations in load. It seems hardly possible that through the ages during which humanity depended on windmills for its bread, no one bothered to deal empirically with variations in grinding power due to irregularity of the wind. The author has inquired into this and discovered an answer, what cannot be claimed as the first in the field. Long before him there existed a retroactive mechanism in windmills, the bale ball, which regulates the grain delivery from minute to minute in response to the requirements. The HEBILLE, the L-pounds MILL, HOPPRPROGNITOROFREPROACDIO, and a description of this mechanism was found in the Encyclopédie méthodique d'arts et métiers mécaniques of 1786 in the chapter on windmills. Bertrand Gill, in a later study of the history of technical processes, was able to trace it back to 1588, the date of publication in Paris of a book entitled Divers Artificios Machines, written in Italian by Romelli, the military engineer of the time of Henry II. This work describes a similar 116 device used in water mills. Here was a governor antedating that of what by at least 2 centuries. The grain distributor has always been called a bale ball and consists of a wooden chute which guides and delivers the stream of grain. The end of this chute rests directly on the driving shaft of the mill, which at this point is squared or encased in a more or less square box whose edges are strengthened with metal. At every revolution the bale ball received 4 knocks, each of which makes some grain fall out. In modern mills this principle is termed a shock distributor. When the wind increases, the mill turns more rapidly and will receive more grain. With less wind, the feed will be diminished. At first sight it might seem that this mechanism is another version of Watt's regulating principle. When, for example, the sales factor is diminished because gales have torn away some of the sailcloth, the mill will slow down and receive less grain. This will allow it to recover some of its former speed. If the resistance of the grain is increased, as may happen if some stones or grit get in with it, the mill will have to increase its power, which it will do by diminishing the grain supply. As far as the wind is concerned, the rate of revolution is most certainly not stabilized, for it will continue to depend on the wind. It might even be urged that here is an example of a servo mechanism controlled by the wind. This would mean that the system could compensate for disturbances affecting the sails or for hardness of grain, but not for variations of the wind's force. This is wrong. The wind force is a factor, not a controlling force. It is not through its effect on the grain delivery that it turns the sails of the mill. Here is an ordinary feedback system, derived from the speed and acting on the grain supply as the following diagram shows. But the factor of application is not strong enough to cancel the effect of variations of speed due to wide variations in the wind force. The feedback which is sufficient to compensate for variations in the lesser factors sail efficiency, hardness of grist is unable to compensate for the wind factor. It can govern all the factors but one. In water mills, for which this system seems to have been primarily designed, the feedback is not called upon to make great variations in grain flow. since the water is always regulated by a sluice gate and the only important variable. RETROOCTION, THEFECRETOFNATURIDLCTIVIVY. 7. THINKINGBYM factor will be the hardness of the grain. If this system is unable to fulfill its compensatory function as far as wine force is concerned, it shows another function of retroactive linkages which is not always so easily discerned in other examples. It binds all the factors to that of the factor of application through the effect, making this dependent on each one of the other factors and thus on all of them together. Here, the grain supply depends on the wind through the factor speed so that the grain supply is always related to the wind requirements. This secondary function of feedbacks, of harmonizing two factors through the same effect, seems to occur frequently in physiology. In respiratory regulation, the amount of oxygen breath in is always proportional to the amount of lactic acid formed through muscular metabolism, that is, to the effort made. One is therefore entitled to think that the true function of this feedback is not so much an attempt to control the amount of CO2 in the arterial blood, which is not an end in itself, but as a means of regulating the supply of air to the needs of the muscular mechanism. Chemical equilibria. We find the retroactive mechanisms of our artificial machines in physiological mechanisms. We find them indeed in all man's activities, whether he thinks, or works with his hands, or directs the machine. The man-machine retroactor accumulating the corrective power of feedbacks in his own memory or in the program of a mechanism. It would even appear that retroaction is the fundamental property of nature which tends to maintain its orderly equilibrium under all conditions. 118. RETROCTION, THEFECRETOFNATURIDLCTIVIVY. To instance chemical equilibrium, at first sight it is difficult to realize that the laws governing this are the same as those applicable to widely different phenomena. In fact, they are only the expression by chemists, in their own field, of logical principles that are universally applicable. If a reaction is reversible, that is to say, if the compounds produced by it can be restored to their original form, equilibrium is established between the tendencies to combination and dissociation. To give an example, let us take the formation of an ester from an alcohol and an acid esterification. This reaction has reverse process hydrolysis. These two reach the state of reversible equilibrium, symbolized in chemistry by the sign acid plus alcohol 5 * ester plus water esterification hydrolysis. The effect to be considered is the proportion of ester or alcohol in the mixture. The more ester, the more hydrolysis will take place and the less esterification. But the factor esterification, which increases the proportion of ester, is positive and the factor hydrolysis which diminishes it is negative. There is therefore a positive retroaction on the negative factor and a negative retroaction on the positive one, that is to say, the state of equilibrium. Even if we did not know from experience that equilibrium is established between these two reactions, it would be implicit in logical analysis, which illustrates the fact that the logic of THINKINGBYMCHINE effects is an essential form of approach to knowledge. Even if we did not know how to increase the proportion of ester, the above diagram should leave us in no doubt that we must cross the messages, acting positively on the positive factor and negatively on the negative factor. This is precisely what is done in commercial ester production. Water is removed as fast as it is formed to inhibit hydrolysis and alcohol is added to increase esterification. The natural constancy regulation is replaced by an artificial tendency regulation. What is the point of equilibrium? This is a general question of negative feedback whose answer in chemical terms is the law of mass action of Goldberg and wattage. The reaction will effectively cease when the direct and reverse reactions are equal in velocity. If instead of velocity we say differential coefficient or slope of a curve, we begin to discover that we are dealing with a particular case of the universal law of equilibrium of the effect in negative retroaction. In a similar case, the equilibrium of the amplitude of the counter-reactions is expressed in the formula E equals circumflex accent, where the increase in amplification but is the reciprocal of the reaction R. But at this stage we may not go into the law that proclaims the balance between tendency to variation of the effect and retroactive correction. For the purposes of a popular exposition, many such paths leading to cybernetic byways, however tempting, must be ignored if the discussion is to be kept within reasonable bounds. In a chemical reaction, the attainment of equilibrium is not, however, always entirely determined by the amount of reacting bodies present. If their reaction modifies temperature and pressure, these must be considered. In such cases the law of moderation of Van 't Hoff and Le Chatelier may be stated thus: when any influence or factor capable of changing the equilibrium of a system is altered, the system tends to change in such a way as to oppose and annul the alteration in this factor. This almost amounts to a definition of negative retroaction. Consider a salt in the presence of a saturated solution of the same salt. When the temperature rises, an additional amount of the salt will be dissolved. This is so because solution is accompanied by absorption of heat. It is an endothermic event. According to the above-mentioned law, the only change in 120 the system possible is one that will compensate for the increase of temperature by heat absorption, and this is effected by increased solution of the salt. The absorption of heat depends on the effect solution. It acts as the detector. It retroacts on the temperature factor in order to diminish it. The law amounts to this, that the retroactive message must always oppose any variation of a factor, if a system is to maintain its equilibrium. That this is so we have already learned from the low GICOF effects. To take yet another example, consider the synthesis of ammonia from nitrogen and hydrogen, which is a reversible reaction and hence only gives a small yield. The synthesis, however, is accompanied by a diminution of volume. An increase of pressure would therefore be a favorable influence. Actually, commercially produced ammonia is subjected to very high pressure. In this case we have an example of a servo mechanism. The effect, the yield from the synthesis, is stabilized as in the example of esterification, but its equilibrium point is dependent on the pressure. In order to demonstrate the validity of a law by the logic of effects, one must give an AC count of the system which allots appropriate values to the factors involved. If this yields a stabilized whole, then the validity of the law may be considered proved. If we examine this synthetic method in the light of the law of Van 't Hoff and Le Chatelier, taking the yield as the effect, the pressure factor must be F, since according to the law an increase of pressure increases the yield. This may be shown diagrammatically. RETROCTION, the HEFECRETOFN ATUR IDLCTIVIVY 12I, the HINKINGBYM the CHINE. This system, giving us a negative retroaction which is stable, demonstrates the law. Vital equilibria. We may next consider a similar system of interpretation in the case of vital equilibria such as were studied by the great mathematician Vito Volterra, the creator of modern functional analysis. Such vital equilibria are built up between different living species where one lives on the other and are demonstrable not only between the fishes and worms of a pond but between man and nutritive plants. Let us think of a pond containing goldfish and worms. The more fish it contains, the more worms will be eaten. The supply of worms diminishes and the fishes die of starvation. If, on the other hand, the worms increase greatly, they will feed more fish which in consequence will take a greater toll of the worms, and so equilibrium is set up between the two populations. This equilibrium is that of an effector set for unvarying work governed by negative retroaction according to the dual scheme depicted below. Worms. This equilibrium involves hysteresis. Action and reaction do not compensate instantaneously. It is always possible for one side to gain the momentary advantage. Volterra studied the case of certain soleils and sharks in the Adriatic, an almost 122 enclosed sea, where the two types of fish dominate alternately. Yet another such cycle may illustrate the matter even better. In a certain region of northern Canada, the foxes prey entirely on rabbits and the rabbits have hardly any other enemy than foxes. But there is always some variation round the point of equilibrium which is never actually found. For about 4 years the rabbits lead, and then for the next 4 years it is the turn of the foxes. When the foxes are too numerous, so many rabbits get killed that the race is on the point of dying out, and then the foxes, left with nothing to eat, die off in turn. Then, with no enemies, the few rabbits are able to proliferate in peace to such an extent that the few surviving foxes, with an abundance of food, are again on the increase, and the cycle begins once more. In just such a way does a machine with an ill-adjusted regulator start hunting. WHER logic destroys mankind. Economic and demographic phenomena are governed by retroaction. famine may be looked on as a vital case of adjustment to equilibrium, if we consider the ration of food per person as a stabilized effect dependent on two factors, one positive, the amount of food available, and the other negative, the size of the population. Any variation in the effect modifies the population factor positively. RETROCTION, THEFECRETOFNATURIDLCTIVIVY. But, going to a special type of arrangement, the effect has not the same retroaction according to whether it increases or diminishes. When the ration per person increases, it can only lead to a slow increase in population, whereas in the reverse direction it acts much more rapidly and brutally. It is 123. THINKINGDYMCHINE. Obviously quicker for a man to die of hunger than to live and bring up a generation of children. If the factor available food supply is not a strong one and the population is always undernourished, any sudden diminution of its resources, such as a bad harvest, will set up a brisk retroaction to diminish the number of mouths to feed. Famine is thus the reactor of a negatively regulated system. Its fatal influence colors the picture drawn by the logic of effects. We have just used the term negatively regulated. It might be said that it would be better to speak of faulty regulation. As a matter of fact, it would be better not to use such terms as regulation and faulty regulation and useful effect at all. They are all linked with the notion of an artificially ordained end goal, the purely anthropomorphic concept. An effector always tends towards equilibrium, whether this be one of constancy or tendency. It is a matter of indifference to the logical process of reasoning whether its laws favor human good or lead to human disaster. The freaks of the law of supply and demand may give rise to retroaction that is sometimes favorable from an anthropocentric point of view and sometimes unfavorable. It is easy to present this law in logical guise. The supply offered is a negative factor. As it increases, it causes a lowering of prices, whereas demand on the other hand is a positive factor. The law which this illustrates affirms that a rise in prices increases the offer of supplies and diminishes the demand, thus bringing 124 back the price to the point of equilibrium. The diagram makes it sufficiently obvious that this is an example of negative retroaction. But from the human point of view, the two reactions have very different values. The increased supply is desirable, but restriction of demand, if the food in question is vital, may result in famine. Thus of the two types of regulation which are jointly exercised in the same system, one may be ideal and the other catastrophic. Stable and unstable equilibria. It is sufficiently obvious that any system endeavoring to establish an equilibrium must be regulated by negative retroaction, but a role of positive retroaction in natural conditions is less evident. This is perhaps due to the fact that we have given less attention to it in the machines where it exerts an influence. Consider the watt regulator acting with a positive retroaction. To effect this, it is enough to change the position of one of the levers which connect the ball weights to the steam valve, thus reversing its action. It will now no longer ensure moderation in activity, but will condition frenzied overactivity. The machine will now aim at an apparently insane end goal as assiduously as it previously sought to ensure a sensible performance. It will cut off power when an increase of work demands greater effort and increase power when work is light. Cutting down the steam supply with increased work, it will obviously soon stop functioning altogether. Increasing it with little to do, it will race to destruction. Much the same sort of thing would happen in all other machines designed for continuous work, if the direction of the feedback were inverted. Alteration to the regulating device of a water tank would cause it either to run dry or to overflow. In the boiler, the water would become either too cold or boil over. In radio sets, anti-fading would become pro-fading. The rolling mill would produce sheet metal becoming progressively thinner and thinner or thicker and thicker. The carbons of an arc lamp would separate as soon as the current was switched on, and in the case of the greatest triumph of feedback, the automatically controlled anti-aircraft gun, the fire would be diverted from the enemy as soon as his plane. RETROCTION, THEFECRETOFNATURIDLCTIVIVY. 125. THINKINGDYMCHINE was cited. All this would happen if the directions of the lever H or the current were inverted. The twofold diagram will make clear both the similarities and the differences between the two types of retroaction. If a ball is placed on a concave surface, it will come to rest at the bottom. If it be displaced, it will at once return to the same position. The force exerted in the displacement carries it back to its stable position. It is in fact a model of retroactive equilibrium. If the ball is placed on a convex surface, even if we succeed in placing it on the summit, it will not remain there. The least disturbance in any direction will cause it to roll down with increasing speed. Thus a governor with its reaction reversed will either stop the machine or overrun it. The diagrams of these balls are remarkable models of stable and unstable equilibrium and much more illustrative than the usual symbols of a cone standing on its head or on its base. Obviously it is the displacement from the equilibrium position which gives rise to the restoring force when the cone or the ball is in a stable situation. Deviation leads to its own cancellation. There is negative retroaction. Equally, in the unstable situation the slightest displacement sets up a force leading to more displacement. Deviation leads to its own increase. There is positive retroaction. As a broad generalization, it may be said that equilibrium is stable if the retroaction is negative and unstable if the retroaction is positive. It now seems that the law of regulation which remains applicable to machines, can appear also as a law of equilibrium in which constancy corresponds to stable, tendency to unstable, equilibrium. Thus the importance of retroaction for natural phenomena is even greater than might appear at first. Negative retroaction, positive retroaction plus stable equilibrium, unstable equilibrium. 126. Cite, the two types correspond respectively to stability and instability. In addition, negative retroaction explains the principle of least action or the principle of Maupertuis, which is one of the fundamental principles of the universe. The pebbles on RETROCTION, THEFCCRETOFNATURIDLCTIVIVY, the bed of the river lie so that they will offer the least resistance to the stream, as do the scales of a fish or the hair of an animal. A floating stick lies in the direction of the current. In the same way light finds the shortest path. Let us take two positive factors, the field of force and the angle at which a moving body cuts the lines of force in the field. The reaction of the field and the moving body may be considered to be the effect. This effect retroacts on the angle factor and diminishes it when it increases itself. The retroaction is negative and so the system is in equilibrium. This demonstrates the principle of least action. A strange relationship, an OSCILTINGCIRCUIT and an atomic pile. By this time we should all be in a position to appreciate that retroaction is the great organizing force of nature, the important principle of anti-chance, but we have not yet dealt with all its possibilities. Let us again consider the ball in unstable equilibrium on a convex surface. It rolls down, but if it encounters an obstacle on the slope it will stop. We have now touched on one of the great universal governing principles, the positive retroaction, whose effect is stopped when it attains a certain magnitude by some mechanism which may be called a limit. 127. THINKINGDYMCHINE. A perfect example of positive retroaction being used in connection with such limiting organs is that of self-maintained oscillating circuits. The circuit consisting of an inductance and capacity will, it is known, start to oscillate in response to the least electrical stimulus. These oscillations would quickly die away, but if, however, the stimulus is repeated at an appropriate frequency, the oscillation continues. If a positive retroaction enters into the system, the oscillations, once started, continue indefinitely. This is exactly what happens in self-maintained oscillating systems. Consider the retroactive circuit joining the output of an amplifier to its input. There is an alternating current at I volt which is amplified to I volts. A part of the outgoing voltage is returned to the input. Let us say 150 or 2 volts. This will add itself to the input current, provided of course that it is in phase. There will now be an input of 1 plus 2 equals 3 volts, which when amplified gives 300 volts and so on. There is no theoretical reason why the increase of the output should ever stop. Practically, of course, the whole system would blow up. It is here that the principle of limitation comes in. It is not necessarily due to one particular organ, although in most cases it will be provided by the filaments of the amplifier valves which can only emit a certain electronic flow. Such an arrangement is frequently found in spontaneous retroactive mechanisms. The message is of the same nature and acts in the same way as the factor on which it operates. It does not therefore condition a new function, but reinforces that already in operation. The arrows of both the message and the factor tend to converge instead of the message being superimposed on the factor. This mechanism constitutes a perfect electronic analogy to 128 RETROCTION CHEFECRETOFNATURIDLCTIVIVY V++++FJ Sheriff DDR X plus plus J R plus circumflex accent 3F plus triggering current tension amplifier amplified current. An unstable equilibrium such as that of the ball on a convex surface. When the ball is on the summit of the convexity, it does not require even a flick of the finger in order to make it roll down. An imperceptible tremor will suffice to start its fall in any direction. In the oscillating circuit, the situation is much the same. It is unnecessary to feed in a deliberate input current. The minimal induced current that occurs in every conductor will be enough to trigger off the retroaction. In the case of our example, we assumed it to be I volt. Another remarkable example of limiting action is given by an atomic pile. If we think of the uranium of a bomb in its global mass and not in terms of each of its atoms, the fission will appear to be a positive retroaction tending to the production of an infinite effect limited only by the mass of the matter that is capable of fission. The neutrons trigger off the effect, which then increases in snowball fashion. The arrangement exhibits perfect parallelism with the oscillatory circuit. Xi++. Here is an exact resemblance to the unstable ball. The effect and the retroaction are both triggered off by a natural factor acting spontaneously but of minute power, in this case cosmic radiations. In the atomic pile, this fission has to be limited. Cadmium bars absorb most of the neutrons and allow the 129 VHINKINGBYM passage of only enough to keep up the fission process, but not enough for it to become explosive. The cadmium is a limiting agent, but the arrangement is complicated by retroaction which controls the action of the limiting agent. In order to ensure that the cadmium bars should not allow fission to run riot, they are submitted to a control in the shape of a feedback derived from the flow of neutrons. This is a secondary effect that can be detected in the ionization chamber. If the reaction tends to accelerate, it is braked by the cadmium bars, which are pushed a little more deeply into the pile by a motor mechanism. All this is conveyed by the diagram in which the limiting agency has a negative value. Asterisk neutrons of fission T. Cadmium Y J R asterisk asterisk greater than triggering neutrons. _/0 mic / circumflex accent 3 asterisk uranium fission H. In nature, however, limiting action is not a function of one special organ. It depends on the retroactive relationship that only allows the passage of one definite message, which as often as not is that engendered by the coefficient of efficiency of the driving factor. It is, however, desirable to read our descriptions of mechanisms from anthropomorphic implications. From now on it is our purpose to present an abstract picture of these mechanisms. The end goal is a logical concept. When man gives an end goal to an effector, he arranges its factors in such a way that a certain effect will in all probability ensue. This end goal may then be considered as an effect whose probable action has been artificially planned. It is the result of a struggle with contingency. When a machine is provided with interaction or retroaction, its likelihood of attaining 130 the end goal is enhanced since this probability is increased by guarding it against chance variations of the factors. But the operation then seems of a different type inasmuch as it is not primarily determined by the values of the factors. It depends on the internal organization of the effector. This internal conditioning of the end goal is also found in nature. But in natural processes an end goal due to the action on the factors of predetermined values is hardly conceivable from an anthropomorphic viewpoint. In the days of classical mechanics, only one way of reading the effect from contingency was known. This was by very rigid predetermination of the factors. Observations based on machines of this nature made it appear inconceivable that natural effectors could use the same type of mechanism. Now, however, we recognize that linkage between factors and effects can organize the effects independently of the functional determinism of the factors, so that it is easy to realize that natural processes have their own way of combating contingency. All interpretations of end goal attainment by natural effects appeared to be logically inexplicable, so long as it was thought that the end goal could only be reached by predetermined factors. We now know that nature has other means of ensuring that an effect should have every chance of accomplishment. Nature does not act along the rigid lines of strict determinism, but possesses to a great extent the power to protect its processes from chance interference. Between these two extremes there is room for innumerable philosophic doubts. It is a purely mechanical device, the Watt governor, which offers the solution to the problem. It has shown that certain effects are stabilized by their own action. Millions of effects are actualized around each of us. They may have varying degrees of importance. They are contingent. But if one of them acts on one of its factors, thus establishing its own particular value, it is no longer the product of chance. At that moment, two elements that we distinguished in the attainment of an end goal are united, a certain effect and a certain value of this effect. The effect that in our self-regulating machines we pronounce as being useful, whose utility we recognize in physiological mechanisms, is the effect that retroacts. The value, the purpose of the end goal, constitutes RETROCTION, the HEFCCRETOFNATURIDLCTIVIVY, the HINKINGBYM, the CHINE. The 0 point of negative retroaction. The ideal of an end goal considered as a metaphysical concept, and as such frequently denied not without justice, is entirely re-established when seen from this logical point of view. If a system tends to achieve a certain effect with a high degree of probability, this effect is its end goal. The end goal of an effector is a certain effect whose probability is much greater than if it were dependent on mere chance. All end goal results postulate the struggle with contingency, an anti-chance organization, which may take either of two forms. The artificial end goal is achieved by the strictest possible determination of its factors. This is typical of mechanisms. The natural end goal is achieved by appropriate organization of the inter- and retroactive linkages between factors and effect. It is characteristic of the living and mineral worlds. Between one or other of these methods there is, however, nowadays, no fixed division. The artificial often conquers the natural type, and this revolutionary process, the cybernetic revolution, is not only to be found in material processes but in the manner in which we view life. The tree grows up towards the light. We may be invited to admire the teleological character of nature. Others may tell us that the behavior of the tree was rigidly determined. This age-long discussion between the two schools of thought seems to be futile as soon as we realize that this natural phenomenon is not due to goal-seeking nor yet to external stimuli, but to the internal constitution of the effect. The tree threw out effects on all sides in the shape of branches, but it was the branch that got most sunlight which developed the factors that caused it to grow, and it will continue to grow as if the sun drew it up like a magnet. This we call a positive retroaction, or an effector with a positive tendency, for the tree is heliotropic. The pebble that is rolled about by the movement of the seed tends to assume a smooth surface that will aid further rolling. The effect here is the movement of the pebble, which retroacts on the resistance to movement factor, rendering it continually less resistant. The more the pebble rolls, the more it wears. 132. Away its irregularities, so the better it rolls. An example of positive retroaction, the pebble tends towards the annulment of its resistance. We need neither determinism nor teleological phenomenism, but the internal constitution of the act itself, a constitution that can overcome contingency. Let us now look at some more complex cases. FROM bus QUESTOINDINFDAMNES. What person, queuing for a bus, has not, at some time or other, burst into a flood of invective against the bad organization of the transport system? The wait of 10 minutes and then 2 or 3 buses will roll up almost bumper to bumper. It does no good to lose one's temper. Let us look at it instead as a good example of retroactive effect. If, for any reason, a bus starts to fall behind its time schedule, its lateness will get worse. The effector omnibus A is so arranged that its journey will RETROCTION, THEFECRETOFNATURIDLCTIVIVY be accomplished in a given time. Its factors have been made just as well as possible. The factor length of stops depends on three prefactors: I. The number of passengers who get off, 2. The number who get on, 3. The number of passengers standing inside the bus. These three prefactors are all positive and increase once the bus has started to run behind schedule. The later it is, the more passengers it will find waiting at each stop, and the more crowded the bus is inside, the longer the 133 THINKINGBYMCHINE passengers will take to get on. Retroaction plus on plus by F equals F. The delay will tend to increase. The bus be thought to have followed 5 minutes later, but not having had an initial late start, it arrives at the stopping places less than 5 minutes behind the other. There are fewer passengers, therefore they get on and off quickly. The bus now begins to gain more and more time until it will finally catch up with bus A. Its schedule was exactly the same as TS, but in the one case the effect tends to increase and in the other to diminish. Both effects are due to the initial disruption. In one case the unstable ball has overbalanced on one side of the convex curve and in the other case on the opposite side. What is the remedy? To act on one of the positive factors of bus A inasmuch as one cannot prevent the passengers getting off, nor remedy the obstruction of the exit, the only solution would be to take up no more passengers at the stops and thus accelerate A and slow down B, by leaving it the surplus of passengers to pick up. Conductors actually do this sometimes to the great indignation of the queue of waiting passengers who do not understand the mysteries of positive retroaction. From comedy to tragedy. In India, vast irrigation schemes have been undertaken to overcome shortage of food supplies due to drought. The first results, however, were disappointing. The quantity of food increased, it is true, but the more food that is available the lower the death rate. The population increase offsets the increased food supply. There is a retroaction of the average person's ration on the death rate positive prefactor. When the ration increases, the death rate decreases. We have then J on plus by equals. The effect average ration thus tends to be stabilized, especially when the irrigation factor affects the death rate through improved sanitation. We have thus a serious situation in which the remedy leads to its own destruction. The logic of effects will permit the difficulty to be overcome. The feedback acting on the death rate prefactor will tend to stabilize the average ration effect in spite of the increase of the prefactor on irrigation. We must offset this retroaction. But we know that feedback is impotent to control a tendency once a factor varies beyond certain limits. In such a case it cannot compensate for the deviations arising in the 134 RETROCTION, THEFECRETOFNATURIDLCTIVIVY effect. The irrigation prefactor would have to increase very suddenly for the resultant deviation of the effect to exceed the compensatory power of the feedback. That is to say that of the coefficient of efficiency of the prefactor death rate. This is the situation pointed out by the English economist Malthus. Mountains and forests. When a mountainside begins to crumble away by erosion, it is an ever-accelerating process and the resultant deforestation, after a gradual start, will increase rapidly. Vegetation, the only factor that combats erosion, is eventually destroyed by it. The surface water running off, which is the chief cause of erosion, gathers speed, thus furthering the process. There is therefore a double positive retroaction. The process can then only tend towards final disaster. The theory of effects makes the interpretation of this retroaction quite clear. In this case the tendency is unequivocal. The only reservation that need be made in a prophecy of ultimate disaster is that contingency is not likely to affect the factors involved beyond certain limits. If we consider a stretch of country covered with a vast virgin forest, we are pretty safe in prophesying that some 1,000 years hence, though the forest may still occupy the same area, it will be no less dense. Apart from climate, 6 other factors contribute towards afforestation: seeding, fertility, 135, THINKINGBYMCHINE, of the soil, humidity, firmness of soil surface, shelter from gales, and, lastly, sufficient space, that is the space necessary for the trees to spread their roots and branches. These are all favorable or positive factors. The decisive years for the future existence of the forest are the earliest. It is true that all the first 5 conditions may not be fully met until once the forest has succeeded in establishing itself, when its further development is assured. The forest effect retroacts positively on the 5 factors with a tendency to increase them. The more trees, the more seeds, the more humus from fallen leaves, the more fertile the soil, and the more undergrowth, the damper the soil, and the more roots, the less likely is soil erosion with its resultant denudation, and the greater the number of trees, the more shelter from the wind there will be for each of them. For all that, the forest will not be able to exceed a certain maximum density. Stabilization is achieved by a negative retroaction on the Lebensraum. The more trees there are, the less space for the growth of each one, and there will be more young stunted trees stifled by overcrowding. A force of 5 positive feedbacks promotes the development of a forest of ever greater density, but at the same time the negative retroaction begins to make itself felt, and when the forest reaches the stage of full development, a negative feedback stifles the trees and prevents too great an increase of density. Such a combination of retroactions could successfully combat the usual climatic variations, were it not for certain accidents. 136. RETROCTION, THEFECRETOFNATURIDLCTIVIVY, for which no feedback can compensate and which displays the factors beyond the usual limits of tolerance. Extremes of heat or cold may kill the trees or at any rate inhibit their germination. The new light on political economy. The theory of effects should help in the study of economic phenomena and the prediction of their evolution. It is here that cybernetics reassumes its original role, that of Plato and Ampere, the science of social government. This definition of the aims of cybernetics made by Ampere is very much to the point: to seek out causes, to study effects, to foresee and enhance results by continually taking account of the mutual dependence of cause and effect. For example, some economists praise the mechanisms underlying American prosperity, while others condemn them. Mass production allows low prices and high wages. This gives the public high purchasing power and creates prosperity. An increased output calls for an increased demand. This would seem all to the good, since mass production promotes prosperity and with it an increased demand. Such is the mechanism of American prosperity, above all in post-war periods when the demand for consumer goods is very high. 137. THINKINGDYMCHINE JR**V01**+++++ demand for manufactured goods. Amount of ++D, F. F plus.J, goods possessed OT manufactured goods plus circumflex accent tilde circumflex accent. Low prices \V++. The backslash circumflex accent +++4 ++T V greater than I mass production high wages. Circumflex accent 1 I1 TJ** purchasing power general prosperity. The effect purchasing power retroacts on the demand factor, for it increases the demand. Since all is positive, prosperity should continue to increase. But can the retroaction continue indefinitely without limit? The feedback has a limitation in the quantity of goods possessed, since this would evidently limit demand. The power of this limiting agency depends on the effect prosperity. The greater the prosperity or the greater it was in the immediate past, the more the limitation acts in restraining the retroactive demand. So that here the negative feedback governs the action of a positive feedback. The mechanism is very like that of an atomic pile. This is a curious parallelism that seems to show American economists to be right in holding that their system of ever-increasing prosperity can never collapse. But this example, however much it may accord with logical expectations, does not take into account the actual practical conditions. Atomic retroaction has only a very small hysteresis, but economic effectors are very slow in action. As a result, equilibrium can only be achieved after much oscillation. Just as in medicine the disease itself has always some part in establishing the cure. When the oscillations develop in a direction that is contrary to prosperity, we have a state of crisis. The situation becomes very complicated owing to the great difference in latency of the two reactions. The positive retroaction acts after a short latent period, As soon as the worker receives his pay he hurries off to spend it. In fact, he often anticipates it by buying things on hire purchase or at shops that allow credit. The negative feedback, on the other hand, only becomes fully operative after some years, a period long enough. 138. For the accumulation of sufficient possessions to bring the limiting agency into play. Whence there starts a cycle of interference between these retroactions whose interplay is not readily harmonized. If it is true that the system can always regain equilibrium, it is equally true that such equilibrium can only be attained by economic crisis. For average prosperity to be maintained, prosperity must occasionally diminish. Thence arise those cyclic variations that play such an important role in a MER like an economy. The UT1 meter U street MDRTH. The T each new point of equilibrium is a little higher than the preceding one. There is, however, a danger that aggravates the critical periods of the system. The diminution of the mass production factor required by a periodic adjustment of the effect leads to certain difficulties. Factories organized for mass production cannot reduce their output without setting up internal difficulties which will have repercussions on the entire economic system. Economic phenomena produce so many effects and have so many interrelated complex factors that any disturbance of an end product is bound to influence some factors, and when this happens there will be some retroaction. But retroaction implies hysteresis and hence equilibrating oscillations. Since economic effects only make their presence felt after long delays, the whole economic system will exhibit slow periodic swings, and whenever the reaction which tends to smooth out deviations assumes proportions that threaten human welfare, we have periodic crises. The theory of effects may in fact be illustrated by the 7 fat kind and the 7 lean ones. All this naturally leads one to question whether the occurrence of these crises is inevitable, whether government action could avoid them by appropriate interference at chosen points in the economic system. They certainly cannot be avoided if economic mechanisms are allowed a free hand. But if, however, interrupting or breaking the retroactive linkages is carried out by administrative action, the oscillations can be damped down and the potential danger to mankind reduced. The theory of effects can play an essential role in the government of an economic democracy. Planned, or at any rate corrected economy is seen from RETROOCTION, THEFCCRETOFNATURIDLCTIVIVY, I39, DHINKINGBYM This standpoint to be more conducive to stability than laissez-faire. Further researches from this angle would be a fascinating study. One would see that the 19th century policy of laissez-faire played its part in stimulating the positive retroactions in the upsurge of prosperity. It awakened the world economy. Without it and without the complex of tendency effects that it set free, the world would never have known the enormous rise in the standard of living that we now enjoy. But its feedbacks have always engendered certain reactions of which our social consciences can no longer approve. The theoretical justification of famine will never induce us to admit this as a means of economic stabilization. The mechanism cannot be left free to destroy man, even for the sake of the eventual welfare of society, of those who are not destroyed. One must intervene to suppress the ill effects of a retroaction and to enhance its benefits. Now that the great economic machine is working throughout the world, it is imperative to control those retroactions which created prosperity at the price of so many economic crises and so many social upheavals. The 20th century must be the age of planned economy, at any rate in the more highly developed countries. But just to what extent should the economy be planned? Since the natural end goals of economic systems may be adverse to humanity, an artificial end goal may have to be fixed. The factors may have to be adapted so as to produce a predetermined effect, and evolution in the economic field may prove to be the reverse of mechanical progress. Such rigorous intervention as restriction of economic factors is theoretically conceivable, but as a matter of practical experience it is obvious how impossible it would be to maintain a close economic control. Some factors would be bound to escape. The knowledge that would enable all factors to be evaluated and controlled is not yet even available. Such an economic system would exhibit the same defects as the classical machine. It would be blind, unable to adapt itself to circumstance, and would become paralyzed if the smallest link in the mechanism were to fail. Liberal doctrine, on the other hand, seeks to accord absolute liberty to both retroaction and interaction with a view to establishing the condition of equilibrium. It would like to look 140. on the economic system as a physical effector, like a river that is seeking its own level, or an astronomical system working through attractions and repulsions. No matter if the river grinds the stones, or the sun disintegrates the atomic structures. Between the classical machines with fixed factors and the physical effectors whose factors are governed by the effects, nature offers a third way, that of life. Life whose factors are fixed within certain limits, but whose effects retroact in order to ensure the synergic action of the factors towards a definite end goal. Thus it is possible to reconcile within the economic system both determinism of the factors and the interplay of natural tendencies towards equilibrium. Mechanisms that would seem to be ideal models for an economic system are the atomic pile, the forest and animal life. All these make use of the efficient regulatory mechanism of positive retroaction, with its tendency to make continuous progress but keep also a negative control. They represent an alliance of the positive dynamic influence and the wisdom of negative retroactive control. The secret of the stars' retroaction could be found in the universe of the stars with their mutual attractions. The phases of the moon might be looked upon as a slight irregularity which characterizes the mutual relation of the revolution of the moon on its axis and its revolution round the earth, a concordance established by double interaction. The stabilizing of a star between the natural repulsion forces of its atoms and the attraction of gravity would seem to be a similarly organized system. Even the pulsating stars of the Cepheids may well be simply instances of faulty regulation. To turn to another problem, we have all wondered how it can be possible for the stars to radiate so much energy without exhausting themselves relatively soon. This was an insoluble problem when men knew nothing of nuclear chemistry. Today we believe the problem to be resolved. The secret of the stars lies in positive retroaction. The contraction of matter, in itself a retroactive phenomenon, raises the temperature. High temperatures set up violent thermal agitation. The hydrogen nuclei thus attain sufficient velocity to overcome the repulsion. RETROCTION, the HEFECRETOFN ATUR the HINKINGBYM the CHINE. That separates the atomic nuclei one from the other. Collisions occur and matter is transformed into energy, that is to say into heat. It is heat that sets off the nuclear reactions. The effect reinforces one of its factors. Thus a cycle of tendency is initiated. One actually, however, the heat does not all retroact in these nuclear reactions. Much of the liberated energy is radiated and only the remaining portion retroacts. It is only when the energy begins to radiate less rapidly than it is liberated, that the nuclear phenomenon will tend to increase. Up to that point it will tend to slow down. It is again the story of the ball rolling down one side or the other of a convex surface. It might be asked why, in the case of the sun and the stars in general, there is not a constant tendency towards slowing down. The answer is that their mass tends to inhibit radiation. The energy given off from the center of the sun obviously cannot escape as easily as that set free at its surface. There is, therefore, a critical mass beyond which the retroaction of the nuclear heat reaction cannot be increased. That is why stars composed of a fragmented mass cannot exist. That is again why an immensely powerful H-bomb could never destroy the Earth in a single enormous retroaction, since our globe is far below the one should note that pressure is not involved in this cycle. It does not play a part formerly attributed to it, but merely one of triggering comparable to the initial slight push that sets a ball rolling down a convex slope. 142. Critical mass. Hans Bethe has calculated that the mass of Jupiter would not be sufficiently great for the production of energy to exceed its emission, that is, for its temperature to start increasing after an atomic explosion. Logically, then, the mass of a star can be regarded as an element of the message, an element with a positive value. In answer to the question as to whether our sun is on the ascending or descending slope of positive retroaction, the recent theoretical considerations of Hoyle and Littleton seem to show that it is not cooling, as was once thought, but, on the contrary, is in the state of heat. The expansion. Terrestrial life will not perish from cold, it will be burnt up. For some millions of years to come, the cycle heat speed of nuclei, collisions, nuclear reactions, liberation of energy, heat may multiply the sun's temperature 100-fold. Is there any limiting factor to save the world from this infernal cycle? The nuclear reactions of the sun involve a positive retroaction. the cycle of beta, which starts from carbon-12 and comes back to it. At various stages protons bombard the bodies previous formed. Starting with carbon-12, we get, in order, nitrogen-13, carbon-13, nitrogen-14, oxygen-15, nitrogen-15, and then finish with carbon-12 and helium. BNCROFTSUNIVRSCLLW. Other examples might be cited of phenomena in which interdependent linkages occur between factor and factor or between factor and effect. It may, however, be objected that we have already gone to excessive lengths in drawing upon so many different sciences to lend support to what, after all, are truisms, for we must all admit that the world as we know it is a system of mutual influences. It has, however, seemed worthwhile to demonstrate the universal validity of the law of effects by citing the variety of examples. It is not without interest to note how laws deduced from some typical mechanisms are applicable in the most diverse conditions. One in this connection, ignoring for one Marcel Bohl, as early as 1917, clearly saw the generality of this principle. He wrote in his textbook of chemistry that it applies to the most diverse phenomena. It accounts for inertia, for the mechanical principle that action and reaction are equal and opposite, for the behavior of various chemical and physical equilibria, for electromagnetic induction, for polarization of electrolytic cells, and one can extend it to memory, habit, the adaptability of living beings, the preservation of societies and the law of supply and demand. RETROCTION, the HEFECRETOFNATURIDLCTIVIVY, J43, THINKINGBYM The moment the principle of antagonism of Stephanouil Pascal, let us quote the universal law of Wilder-Bancroft. This almost forgotten American writer presented it in this form in 1912. The chemists call it Lie-Galilean theorem, the physicists the theorem of Maupertuis or the principle of least action, the biologists know it as the survival of the fittest, whilst for the economists it is the law of supply and demand. It might seem that this chapter was written under the influence of Wilder-Bancroft, but we learned only of his existence when the book was finished. It is, however, a logical identity of thought rather than a coincidence. Bancroft announced his law in the following terms: the changes that are undergone by a system are such as will tend to reduce to a minimum perturbations due to the external environment. This formula is of even more general application than Bancroft thought, for, as we shall see, it is true of all animal behavior. To mention the external environment is over-precise, since the animal will be equally concerned to regain its equilibrium after a perturbation of the internal, as well as of the external, environment. This definition of Bancroft's can hardly be termed a law. It tells us nothing of the circumstances in which these changes are effected. The positive retroaction which actually exaggerates the effect of the perturbations is not mentioned. Bancroft contents himself with the observation that, in most cases, a restoration of equilibrium occurs. He does not say precisely when this happens, as he should do in a true law. Thus the equilibrium of price as a result of supply and demand is typical. Equilibrium may be reached or it may not, or it may take place as a reversed process of the sort we became used to in the period of shortage during the war. When prices increase, this retroaction ensures a diminution of consumption together with an increase of supply. If, however, we are concerned with indispensable articles of food, it is not so obvious that consumption will decrease. When people are hungry, they do not consider the price of bread. At the same time, the supply cannot increase because there is a true food shortage. In such cases no retroaction could take place. The double feedback would then break down and price would depend entirely on the factors. 1 Law Review Scientific, 28 September, 1912. 144. Soon, however, this condition would be remedied by the emergence of a double positive retroaction determined by quite a different psychological reaction of the purchasers and sellers. This would be an inflation psychosis. If prices are rising, the purchaser hurries to buy before the prices rise still higher. The seller, on the other hand, is reluctant to sell, in the hope that prices will continue to increase. We know only too well how this double positive retroaction sends prices rocketing. P. Rice stabilization, therefore, according to Supetili and DMAND cannot be adduced as a law, it is more a process. But there are other processes which determine the price level. The only real law would be one capable of indicating when this or that process might be expected to come into effect. RETROCTION, THEFECRETOFNATURIDLCTIVIVY 145 CHAPTRVII. Functional causality. An organized product of nature is at the same time an end and a means. Kant. Arcane effects seem to be privileged. Effects influenced by retroaction and interaction tend to arrange their own organization. One can distinguish two types of effect: direct effects whose effectors are open and reflex effects whose effectors retroact on themselves and can be called closed. The stone falls and displaces another stone, which raises a cloud of dust that is carried off by the wind and finally falls elsewhere. The match lights a cigarette. The cigarette burns. The smoke rises upwards and is blown away by a draft of air. Such direct effects are unorganized. Their probability is merely contingent. They have no definite end goal. If they were the only ruling power in the universe, chaos would result. In such circumstances, the atoms which represent the system in equilibrium could never have been formed from the original nebula. Likewise, the stars whose nuclei have organized themselves by retroaction would have been built up by attracting to themselves particles additional to those which formed part of the original mass. From the moment that a factor combines with another factor or with an effect, the effect tends towards a constant or an extreme value. Such an effector would from then on be endowed with a certain internal organization, and if fully organized in this way, its effect acquires a high degree of probability. This term, organized applied to effects, would seem to be appropriate, founded as it is on the quotation from Kant at the head of the chapter. Kant's dictum might seem to indicate that all organization has its origin in retroaction. It might appear that Kant had some understanding of the great universal print. 146. Supple that the study of cybernetics has enabled us to understand more fully. Kant talked of nature, and that which we find to be organized everywhere around us is truly nature, in the sense that Aristotle means when he defines it as the sum of the orderly presentation of things. Aristotle always emphasizes the opposition of nature to chance forces against automaton. His retroaction order and organization, and nature merely an effect dependent solely on its factors, having no law but chance. If so, then nature is but another name for chance. This fundamental distinction between organization and contingency, between reflex and direct activity, corresponds with yet another of Kant's ideas, an idea taught also by other contemporary philosophers, especially the Marxists' antithesis of organism and mechanism. Mechanistic excludes all internally prompted goal-seeking, whereas organic postulates an internal drive towards an end goal. Thus a metaphysical opposition seems to correspond with a logical differentiation. If the factors be masters and not themselves organized, the effect is a mere plaything of chance. It is the chance result of Aristotle or the mechanistic of Kant. If, on the other hand, the factors are a function of their own effect and the effect acquires its own internal organization and determines the end goal, it is then the Aristotelian nature, the Kantian organic. An open effector would then yield a chance configuration and a retroactive effector one of order. But both common sense and Cournot insist that chance is only possible if the factors do not spring from some common prefactor. Cournot asks, in a sentence that has become classic, if the causal sequences are independent, can an effect be classified whose factors are dependent on a common origin? But we should not forget interaction, which also organizes the effect. We find ourselves, therefore, confronted by four types of effect, each of which may be discerned in its essential nature in the study of phenomena. FUNCTIONALCUSCLIDY. Independent factors. 00 tilde pounds x tilde factors dependent circumflex accent interacting RETROCT on common determinant factors effects. 147. THINKINGBYM The first diagram represents chance and the fourth the establishment of order. Between the two, what is the meaning of the effect whose factors have a common determinant and the effect with interacting factors? We might naturally expect to find a gradual progress from the unorganized chance reaction to the fully organized retroaction effect. We hesitated a long time before postulating such a systematic account, which would in effect imply a cybernetic scheme of the universe. Consideration of the special case furnished by the automatic printing device for cinematograph film led us to assume the reality of such an intermediate process. Progressive organization in the film printing machine. The effect is organized inasmuch as it tends to establish its own value. This value is independent of at least one factor, the density of the negative. No matter whether the film be dark or thin, the positive will always be of the same density. One may surmise in this case that it is the organization of an effect, of its progressive acquisition of freedom from its factors. Such a process is exemplified in the acquisition of independence by living creatures as described by Claude Bernard. If, as a consequence of interaction, an effect becomes freed from a factor, it begins to assume its own specific value which is not necessarily related to the factor. It begins, in fact, to be orientated towards an end goal. If an effector is endowed with double interaction, the effect will be freed from two factors and will become still further detached from the function it pursued in an unorganized state and will be subject to its own teleological process. If the effector is retroactive, the effect will be freed from all factors. It will no longer tend to be a function of many variables. It will have its own absolute value, that is, its own end goal. This is confirmed by the following illustration. In our printing machine the effect is independent of the factor density of the negative, but it continues to be a function of the other factors such as sensitivity of the positive emulsion and strength of the electric lamp. If the film is faster, the positive will be darker, and if the current supplying the electric lamp is diminished, it will be lighter. At least, one might have expected the latter to occur, but in practice the current supplying 148 FUNCTIONALCUSCLIDY. The lamp may vary without affecting the positive. The same source supplies an auxiliary lamp which, shining through the negative, allows the photoelectric cell to estimate variations in density of the negative. The cell corrects deviations by regulating the current in the main lamp by a rheostat. Logically the light factor depends on an interactive message, but the latter is complicated by prefactors of which two are the main supply and the resistance of the lamp itself. The interactive message is itself dependent on the main supply, so, taking the light as an effect for the moment, one must consider any interaction between the prefactors, viewing them as operative factors. If now we go back to consider the machine as a whole, we find that the density of the positive is independent of the prefactor mains supply. Even if the supply varies, the density will not be altered correspondingly. But if the other prefactor, the resistance of the light bulb, varies, the positive film will react to its variations. To take an extreme case, if the filament of the light bulb were to break, the machine could not react and the photoelectric cell would continue to scan the density of the film and to adjust the rheostat without any knowledge that the lamp had gone out and that the film was blank. In relation to the prefactor resistance of the lamp the mechanism seems to be inept. On the other hand, in relation to the prefactor mains supply it works with an almost intelligent precision. Here we seem to have the mechanical analysis of some forms of 149. DHINKINGDYMCHINE. Instinctive behavior. An insect will, in certain circumstances, exhibit astonishingly intelligent behavior, whilst in others it will appear to be extremely unintelligent. All this is explicable if we assume linkages between factors. It is through the interplay of their dependent functions that the effects acquire independence, or an end goal. In the case of a simple interaction, the effect becomes free of a single factor, and similarly a double interaction will free it from two factors. In the case of the film printing apparatus, its organization is intermediate. It is freed to some extent from 1.5 factors. The acquisition of independence by an effect is, then, a progressive process. An effect, whilst of course remaining subject to the causal principle, may yet tend towards a more or less complete independence of its factors. Something of the sort seems to take place in the progressive emancipation of living organisms from the immediate control of their constitutional mechanism. It might be thought that such self-control should be called cybernetic. Norbert Wiener gives his book the subtitle, Control and Communication in the Animal and the Machine. Cybernetics thus appears as the science of the automatic control of effects, which machines are now beginning to acquire. The degree of organization of the effect is not, however, expressed by the number of factors from which it has freed itself. This degree of organization will be more complete when an effect is liberated from a potent factor than when the discarded factor exerted only a weak influence. The coefficient of efficiency of the factor from which the effect is freed will determine its organization, and a further consideration in its assessment will be the extent to which deviations of the effect are corrected.